All right. Get started. Yeah. The screen is not showing anything. Sec. There we go. Hey. Where we are. We'll get started in a few minutes. Hey, I guess we should get started, huh? Okay. Yeah, so this week's test, the first question has to do with electrochem. So I'm going to go over electrochemistry so we can do the first question. And we kind of started on electrochem last week. Okay, the way we started was talking about what was called the potential, right? So you have those E values. Okay, these are the potentials. We call them reduction potentials. So that was very quick review. Okay, the reduction potentials are given in terms of volts. Potential means voltage. Okay, so and then when you add reduction and oxidation, hello, come in. We're just going to get started. Okay, when you put oxidation and reduction potential together, you get the cell potential. So I think we're going to use the same example as we did last week. We looked for the oxidation of zinc, yeah. And again, on the test, you will be given the reduction potentials, the one that they want. So, but remember, this is the old AP, so we don't have this chart any longer. But you can see that these are the reduction potentials, and positive means they're spontaneous. So if you look at the most positive one is the reduction of fluorine. Fluorine loves to become reduced because it is the most electronegative element. So the spontaneity is 2.87, right? Volt. That is the reduction potential because all these are reductions. Now, if I flip this, and I will have an oxidation of fluorine. So if you look at the F minus, if I flip this, right? And it's going to become F2. If you balance it, you put a 2 to balance the number of fluorine, and you put 2 electron here, and the E value will be equal and opposite, yeah? So in this case, it would be negative 2.87, right? So negative means they are not spontaneous, okay? So they're not spontaneous, okay? So positive means spontaneous. Negative means they are non-spontaneous, yeah? Okay, so that's what that is. Next one, okay, that we need is, if you look for zinc, so I was using the example we were doing last week. So if you take a look at that, zinc is actually further down. So I need to scroll down a little bit. So if you look at zinc and copper, they're both here. This is zinc 2 plus, gaining 2 electron, becomes zinc. Okay, hello. And then if you look at copper, copper is actually not in the same frame. So let me zoom out. Excuse me. So we have zinc and copper now in the same frame. So zinc is this one here. And copper 2 plus 2 electron give you copper was this one. So I cannot have two reductions. Again, both of these are reductions. As evident, you can see the electrons are being added. Both are reduction. I have to flip one of them, okay? You have no choice which one to flip if you want the reaction to be spontaneous, okay? You have to flip in such a way that they add up to be a positive delta E, right? The cell potential has to be positive. So you know you have to flip the zinc so that the negative become positive, okay? That's important, right? So let me write both of them out, and then again, you'll always be given in terms of reduction, and you have to decide which one to flip so that the reaction is spontaneous. So back to this, I'll note. So this one here on the chart was negative 0.76 volts. Oops, that's now positive, okay? Actually, let me write them as reduction first, and then I'll flip it. Yeah, sorry. Let me get back. Whoops, I think I destroyed some of this. Okay, it's okay. So zinc 2 plus 2 electron produces zinc. The E was negative 0.76 volt. This is what we saw, okay? And then copper 2 plus 2 electron became copper. The E value was positive 0.34 volts. So if I want to run the reaction so that they occur spontaneously, I have to flip one of them. You cannot have two reductions. There's only one way you can flip. Okay, so there's two reductions. You cannot have two reductions. So you have to flip zinc. There's no choice. Yeah? If you flip the copper one, your delta E is negative. So you got to flip zinc. So I got zinc. So zinc would have to oxidize. And the E value now, because you flipped it, you gotta negate. So now it's positive 0.76 volts, and copper 2 plus stays as is, has its law, and that is your reduction. And you're gonna get copper metal, right, being produced, and that's positive 0.34 volts. So now I can add them. The two reactions now can complement each other. An oxidation has to be paired with another reduction, with a reduction. You cannot have two oxidations or two reductions, okay? Because oxidation produce the electron will be used. Those are the same electron used to reduce. So you have to have an oxidation with reduction. You cannot have two reduction. So your final answer here, after you add them, is zinc to copper 2 plus. And zinc will dissolve into zinc 2 plus, and copper 2 plus will become copper metal. And if you add the two E together, you get a cell potential. So this is the overall E for the reaction, and it's positive 1.1 volts. So think of this as spontaneous. Positive means the reaction is spontaneous. Yeah, spontaneous reactions, E must be positive. We talked about this. And delta G must be negative. Gibbs free energy is negative, and therefore equilibrium constant is greater than 1. So it's important to know that. All right, so now I want to turn this positive. This positive 1.1 means that spontaneous redox reactions produce electricity. Produces electricity. You can think of it that way, yeah? So this reaction, the oxidation of zinc, reduction of copper 2 plus, is going to produce electricity. So before we do anything, I want to write down the equilibrium constant, the reaction quotient. If I were to write the reaction quotient, remember is zinc 2 plus. You cannot include solid because copper metal is a solid. Zinc metal is a solid, no solid. So it's going to be zinc 2 plus over copper 2 plus. That is your Q, okay? And I emphasize by putting the little zero. That means initial concentration. Your equilibrium constant is the same, but the concentration of zinc 2 plus must be that of at equilibrium, okay? Like that. So that's the only difference. So this is equilibrium concentrations. Q's are the initial concentration, yeah? So if I want to turn this reaction into a battery, I want you to memorize that such reaction is called galvanic. So galvanic reactions or galvanic cell is also voltaic. It's also electrochemical. All these are the same as batteries. They're spontaneous reactions that produce electricity. So it doesn't matter how you describe them, these have something in common. These must be spontaneous redox reactions that generate electricity, meaning that They're spontaneous. That generates electricity. Yeah. So essentially, that's what a battery is. Batteries have oxidation and reduction reaction that occur, produce flow of electrons. Okay, so these reactions, delta E must be positive, delta G must be negative, and equilibrium constant must be greater than 1. Now, what is opposite of galvanic spontaneous reaction is something called electrolysis. So electrolysis is the exact opposite. So these are non-spontaneous. The reaction does not like to occur, that favors the reactant. So you actually have to force them. You have to use electricity to force, to drive non-spontaneous redox reaction. Okay, non-spontaneous reduction oxidation reactions, right? So these are called electrolysis. Like the electrolysis of water is not spontaneous. Water does not break down into oxygen and hydrogen. So these reactions have E that is negative. Instead of positive delta V, they have negative volt. That means that's how much electricity is required instead of being produced. This is requiring electricity, right? Delta G is positive kilojoules per mole. That means it's instead of releasing energy, this is requiring energy, and equilibrium constant is less than 1. So reactants are favored. So we have to look at the setup for both of these cells. Yeah, cells are basically a redox reaction. So let's begin with the galvanic one. Okay. So the galvanic one, here's the setup. You will have an anode. An anode is a location, an anode, where oxidation will take place. You also have a cathode, where reduction takes place. So anode is oxidation, cathode is reduction. Usually they're cylindrical, they're just a piece of metal. Usually we use a metal. So in this case, I'm just gonna draw like 2 rectangles, but they're actually a sheet of metal. They can be cylindrical, they can be rectangular. But in this case, I'm using zinc metal. Okay, it's a piece of zinc. Okay, and I'm gonna dip that piece of zinc into a beaker. This is the most generic way to draw a battery. Doesn't really work, but this is how you draw the battery. So on the left side, I have a piece of zinc metal. Okay, why? Because my reaction, remember the reaction we wrote was here. We wrote it down. So let me just remind you here, this one, right? Zinc is oxidized. So I need a source of zinc metal. And that is what this anode is providing. So I'm going to label this the anode. Anode is where oxidation takes place. The other one would be the cathode. Cathode is where reduction will take place. Okay, always. Like an ox, red cat. So on the side, I'm going to write down the stuff that we need to know. Number 1, oxidation always occur on anode. There's no exception, yeah? Oxidation on anode, like an ox. Reduction always occurs on cathode, like red cat. So memorize however you want, but an ox and red cat. Either way, yeah? Okay, that's very important. Okay, so what do I put as my cathode? All right, our reaction actually is zinc plus copper 2+. So I need zinc, which I do. My anode is a piece of zinc. On the cathode, I don't need copper metal. Copper metal is not a reactant. It's not required. So you can put platinum as a piece of metal. It's inert. You can put carbon, like your lead pencil, graphite, because graphite is a conductor. You can also put copper metal. So there's a lot of different possibilities. So I'm going to put all 3 here. You can pick whatever you want, but you do not need copper metal. You need copper 2+. So you need a bunch of copper 2+ in the solutions in the cathode beaker. Yeah, you need copper 2+. And you can see as the reaction progresses, you get zinc 2+. So you can see zinc is being dissolved. So I'm going to come back here and modify my diagram and to show that literally zinc is dissolved and goes into the solution. Yeah, as the time progresses, you're going to get less and less zinc. You're losing zinc metal because they go into the solution as you oxidize them. And here, copper 2+ will turn into copper metal. So over time, you're going to get more and more copper metal deposited on the cathode because you're producing copper metal, right? Where do these copper metal come from? The copper metals come from the copper 2+ that was in the solution. Now they deposited out of the solution as they are reduced. Okay, so the observation, the visual observation is that your zinc is going to lose mass as zinc is oxidized. And on the cathode, you're going to see a deposit, uniformly coated copper on the cathode because the copper 2+ is going to go into the, is going to become reduced to copper metal. Okay, so that's another thing, okay? And then in order to have the electron flowing, you have to use an alligator clip to connect the anode to the cathode. And then usually we pass through a machine called voltmeter to measure how much voltage is produced. So this is a wire. You use alligator clip, connect the anode to cathode. So the next thing I want you to remember that electron flows. Electrons flow from anode to cathode. That's the only direction electron will flow. And this occurs in wire, so period, yeah? So if I come back in here and I label electron, electron will come out of the anode. And it's gonna travel in the wire, passes through the voltmeter, and the electron is gonna arrive at the cathode. Because the source of electron is zinc metal. Zinc is being oxidized. So these electrons come from what? Come from zinc. If you write down the zinc electron configuration, it is argon 4s2 3d10. That is zinc. You see the source of electron is the valence electron, which are the 4s. This is the source of electron. So those are the 4s electron that is being lost on the anode as oxidation occurs, okay? So as zinc becomes zinc 2+, it's going to donate away as it loses the 4s electron. And those electrons are the electrons that go and travel from in the wires, okay? These are the 4s electrons, okay? So they are the one that are traveling across the wires from anode to cathode. What are they doing here? These electrons will arrive here, and what are they used for? They're used to reduce copper 2+. Okay, so the electrons from zinc is here to reduce copper 2+. And that is why you see a bunch of copper metal deposited here. So these are very visual, okay? So I want you to memorize number 2, electron flow from anode to cathode in wire, period, yeah? Okay, number 3. Number 3, we talked about here, we haven't talked about is that one more apparatus that we need is that between the 2 beakers, the anode and the cathode, you need something called a salt bridge, yeah? Salt bridge is a bridge, a connection where salt, which are ions, will flow. And the salt bridge here is usually like a paste. They put cotton swab here and ions travel in the salt bridge. So within the salt bridge, okay, which is this apparatus right here, I'm going to label this as the salt, which is ions, a bridge of ions. Salt bridge completes the circuits and prevents charges from build up. So salt bridge prevent, that's the whole purpose, yeah? Prevent excess charges build up. If you don't have a salt bridge, charges will build up very quickly. Okay, the anode will become, the anode and cathode will be, will have charges that will prevent further electron flow. Salt bridge prevent excess charge build up. So you have to know what salt bridge does. So how does it flow? The cations in the salt bridge, which are positive one, will always flow to cathode. And the anions, you put the salt bridge, you put in the salt bridge. So you decide what you want to put into the salt bridge, okay? But the positive one will flow to the cathode, cation to cathode, anion to anode. and this is memorization, and they flow in salt bridge, not in the wires. Electrons flow in the wires, ions flow in the salt bridge. That's why they call salt ions, right? So I have to pick a salt bridge here. So usually you pick something spectator ion that don't react with anything. So if I put potassium, that would be cation. So they'll go to cathode. So I'm drawing arrows here. If my potassium ions I chosen to use in the salt bridge will flow to the cathode. And if I put nitrate, which is another very inert ion, it's going to flow to the anode. And then they do that so that the charges don't build up. If you take away the salt bridge, the current, the electron, the reaction will stop. The battery will no longer work. It's like a broken circuit without the salt bridge. So it completes the circuits in another sense. All right. Next thing is this V, the voltmeter. I put a V with a circle. That actually has a name. It's called voltmeter. So this voltmeter measures something, voltage. Okay. So number 4, I'm going to put it here. Voltmeter measures delta E for the reaction, the cell potential for the reaction. Okay. And I'm going to put a parenthesis, not delta E naught for the reaction. So there's a difference between delta E and delta E naught. So I want to look at this right now. Yeah. So there's another equation, is this one, delta E equals to delta E naught minus RT over NF ln Q. So this equation, yeah, this is called the Nernst equation, Nernst equation, whatever, yeah. Now this is very, very similar to the one we did in thermochemistry, where delta G is delta G naught plus RT ln Q. So you have to do both of them at the same time. They're the same equation. Is one for thermodynamics, one for electrochem. They are derived from each other. So it's the same reaction. So first of all, we need to know that delta E is non-standard conditions and delta E naught is the standard condition. Yeah, that's what that little 0 means, right? So I'm going to come back here and remind you that when we wrote this equation, we got delta E right here. This is 1.1 is delta E naught. That is at standard condition, okay? So this is at standard condition, which means everything must be 1 molar. All the temperature has to be 25 degrees Celsius, 298 Kelvin. Every single ion is 1 molar. All gases is 1 molar. So if everything is 1, Q must be 1. So Q is equal to 1. Okay. So when you're at standard condition, Q is equal to 1 because look, if I plug in 1 molar for zinc and I plug in 1 molar for copper 2+, well, Q is equal to 1. That's what standard condition means. So if you come back and look at this equation, our delta E naught at standard condition was positive 1.1 volt. Yeah, so this thing here is 1.1 volt right here, yeah? Because that is at standard condition, delta E naught is 1.1. And it is true because when Q equal to 1, natural log of 1 is 0, right? So delta E is delta E naught, which is 1.1, okay? Initially, yeah? Initially when Q is equal to 1. So there's no difference between delta E naught and delta E. Delta E is at any condition, yeah? Okay? So the voltmeter is not measuring delta E naught, it's measuring delta E. So my voltmeter will read 1.1 volt initially. So this voltmeter is going to have a reading of 1.1 volts because that is the initial voltage. It's going to produce 1.1 volt. But over time, 1.1 will become smaller, become 1, becomes 0.9, 0.8, 0.7, 0.6. Why is that, right? So number 5, I want you to know is that, okay, initially Q is equal to 1 at time 0, yeah? as reaction progresses, Q increases. Why does Q increase? Because the reaction is spontaneous. You are going to, equilibrium is gonna favor the right-hand side. Yeah? So it's gonna push equilibrium to the right. Wouldn't that mean Q increases? Because Q is products over reactant. So as reaction progresses, Q increases and ultimately becomes K at equilibrium. And Q becomes equilibrium constant when equilibrium is reached. After a certain amount of time, eventually you'll hit equilibrium. So Q will become equilibrium constant when equilibrium is established. And now I'm gonna go back to the equation. When this happens, okay, the Nernst equation, let me rewrite the Nernst equation again, is delta E equal to delta E naught minus RT over NF ln Q. Don't worry about RT and F right now, just focus on this. We said earlier delta E naught is 1.1. And we say Q is going to increase in value. Now, natural log of something that gets larger, this means delta, okay? Again, when it goes up, delta E must go down. So there's no other way around it, mathematically, right? Q gets larger and larger, so delta E will become smaller and smaller. So delta E initially is 1.1 because Q is equal to 1. But then delta E will become 1, 0.9, 0.8, 0.7. Eventually, it's going to become 0 when you establish equilibrium. So delta E becomes 0 at equilibrium. That's the definition of equilibrium. When E becomes 0, delta E equal to 0. Yeah. So you have delta E naught minus RT over NF, and Q becomes equilibrium constant. So I'm going to put that in as well. So at equilibrium, delta E equal to 0 and Q becomes equilibrium constant. So when you have a battery that has reached equilibrium, that means it is flat. Yeah, battery is flat. Galvanic cell is flat. When battery is flat, there's no more chemical potential energy you can tap into. Battery is flat when delta E equal to 0 at equilibrium. So you're no longer spontaneous. You're 0. You're the cutoff now between 0, positive and negative E. So because of this, my equation is this: delta E naught equal to positive RT over NF ln K. So this equation means that if you know what delta E naught is, in this case, for our example, is 1.1 volts, you can solve equilibrium constant. If equilibrium constant is greater than 1, natural log is positive, E is positive. If equilibrium constant is less than 1, E will be negative, okay? So again, delta E is positive, means spontaneous. If equilibrium constant is less than 1, natural log of something less than 1 is negative, so delta E will be negative, okay? Greater than 1 is spontaneous, less than 1 is non-spontaneous. If you know E, delta E, you know equilibrium constant, you can plug in and solve for it. Now, this is exactly the same thing when we look at the thermodynamics with delta G. So we also said this, okay? This is a standard condition only, which is very limiting. Standard condition means Q equal to 1. Everything is 1 molar. All gases are 1 atm. It's very stupid. Q is equal to 1. So there is no difference between delta G and delta G naught when Q is equal to 1, because natural log of 1 is 0. So, but then again, Q will increase, okay? And let's just go directly. I don't want to go over this. So you set this equal to 0 at equilibrium. So delta G naught now all of a sudden becomes negative RT ln K. So once again, you get this equation you have to memorize, right? So if you know equilibrium constant is greater than 1, G will be negative, spontaneous. They will not conflict each other. If equilibrium constant is less than 1, natural log of something less than 1 is negative. You got double negative, G is positive. Then you're non-spontaneous when G is positive. Moral of the story is you have these two equations that essentially connects equilibrium constant with E and G. They will never conflict each other. Those three things, if you know just one of them, you can find the other two. You have equilibrium constant, you have delta G, and you have delta E. If you know one, you can find the other two. So I'm going to combine the equation together. Here are the three final equations. So the first one is delta G naught equal to negative RT ln K, equilibrium constant. Second one is delta E naught is positive RT over NF ln K. And final one is if you combine 1 and 2 together, delta G naught is negative NF delta E naught. Okay, so you combine them together. If E is positive, G is negative. You are spontaneous. So those are the three consequences, the three equations. Basically, they guarantee you just need to know one, and you can find other two. Yeah. Okay. So it doesn't matter which one you know. If you know one, you can find the other two. All right. So that is important. I'll talk about what N and F is. Okay. We talked about N already before. N is the moles of electron transferred. Last week, we were talking about what N is. Okay. If you have, for example, if X becomes X2 plus, that's 2 electron transferred. If Y3 plus becomes Y, what is the value for N? In this case, between 2 and 3, the common denominator is 6. So in this example, N is equal to 6, because you would have to multiply the 2 electron by 3 and the 3 electron by 2. So 6 electron transferred. Do not add them. It's not 2 plus 3. It's the lowest common denominator or lowest common multiple or greatest common denominator. Lowest common multiple, greatest common denominator, whatever it is, it's going to give you 6. Okay. And what if I have this one? If I have something that becomes 2 plus, and then Y plus electron becomes Y. So what is my moles of electron transferred here, right? So between 2 electrons, let me write this properly. Between 2 electrons and 1 electron, what is the lowest common multiple? Lowest common multiple would be 2. 2 and 1 is 2, yeah? So the moles of electron transferred is 2. So that's how we find moles of electron. 2 and 5 is 10. 2 and 4 is 4. 1 and 2 is 2. 2 and 3 is 6. Right? So that's what N is. And F is Faraday's constant. So we need to memorize the value and also the unit. So I need you to memorize F. Okay? Faraday, you'll be given the constant on the test, but I want you to memorize it. Faraday's constant, it tells you it is 96,485 coulombs per mole of what? Electron, yeah? So let's take a look at a minute what that means, because we need this for electrolysis, okay? Charges in chemistry actually has a unit. Charge is measured in coulombs, not in electrons. It's measured in coulombs. And coulomb had a symbol C, yeah? So this is coulomb. Coulomb is the proper unit for charge. The same way like energy is measured in what? Is in joules. Charge is in coulomb, time in seconds. So we don't usually use the unit for charge. We just talk about electron. So what does it have to do with electron? Well, electron carry charge. So one single electron can carry, a fraction of charge, about 1.6 10 to the negative 19 coulombs. So 1 mole of electrons can carry about 96485 coulombs. Okay, so this is what we call electron charge carriers. One single electron carry a fraction of charge. So 1 mole times Avogadro's number, you're going to carry about Faraday's constant. That's how you get the Faraday's constant. So Faraday's constant tells you that in 1 mole of electron, you have 96485 coulomb. Yeah, all right. So electrons are charge carriers. So when we say calcium is 2 plus, well, that is technically 3.2 10 to the negative 19 coulomb. Yeah, that's what calcium is. So do you rather say calcium is 3.2 10 to negative 19 or just say 2 plus? Right? We want to use 2 plus. It's too difficult to constantly call calcium 3.2 10 to the negative 19. So this is the actual charge. But we don't use the actual charge. We use something called the relative charge. The relative charge is 2 plus because you lose 2 electrons. Same thing with aluminum. Your relative charge of aluminum is 3 plus. Much easier to say. Instead of using positive 4.8 times 10 to the negative 19 coulomb. That's not convenient. How do you say oxide? Oxide is 2 minus. That is the relative charge. Instead of using negative 3.2, 10 to the negative 19 coulomb. Not convenient. Yeah. But charges are in actuality are measured in coulomb. Okay. That's the first thing. Then what is a current then? Current is the flow of charge per unit time. So a current is measured in amperes. Okay. So I want you to know what a current is as well. Electrolysis requires current. So current is measured in amperes. So the unit for current is in amperes. So 1 ampere is 1 coulomb per second. So it's a flow of charge. The more ampere, the more coulombs every single second flows through a particular point in time. So current is the flow of charges, which is flow of electrons. So in the wires that you guys have, there's a bunch of electron flowing. So which means bunch of coulombs are flowing through. And if you have current, let's say you have 0.2 amperes, means that you have 0.2 coulombs every single second flowing through a point in the wire. Yeah. Okay. And 0.2 coulomb is lethal. So it doesn't take a lot of coulomb to kill a person. Yeah. Okay. 0.1 coulomb, 0.2 coulomb are lethal currents. So we're dealing with current that's very small. Okay. One ampere is a huge amount of current. Yeah. That will kill somebody, kill elephants. Yeah. So human will die with 0.1 to 0.2 coulombs. So if you have those tasers, you can tase someone. Those are not lethal, right? So it has to be less than 0.1 coulomb. But they can incapacitate you very, very quickly when you have all the charges, electron flowing through your body. So what do we need to know? We need to know charge is measured in coulombs. That's the unit we measure charge. Current is measured in amperes. And 1 ampere is 1 coulomb per second. And Faraday's constant tells you that in 1 mole of electron, there are 96485 coulombs of charges carried by a bunch of electrons. Okay. So those 3 things I need you to know. Yeah. So that is what Faraday's constant is. That's what you have to plug in for F. So if I come back to look at our equation, yeah, our galvanic cell, we're not done. There's more things we need to label here. Right now, I'm number 5. I'm going to come back to this. And even up here, remember we found delta E naught. So if I have delta E naught, I have the equilibrium constant for this reaction. I also have delta G for this reaction. So if I were to elaborate a little bit here, so right here, we talked about those equations. If delta E naught is 1.1 volts, I can use this, I can find delta G, and I can also find equilibrium constant. I just need to know one, I can find the other 2. This is spontaneous, so I expect delta G to be negative. So the formula was negative NF delta E naught. So you literally plug in this one. Okay, so what do you plug it in? Moles of electron transferred, if you look at our half reaction, what is the moles of electron transferred? 2 and 2 is 2. Don't add them, right? The oxidation produced 2 electrons from zinc, and the same 2 electron is used to reduce copper. So the moles of electron transferred is 2. 2 moles of electron transferred. So I'm going to plug in 2 for N. Faraday's constant, well, that's a constant. You plug in 96485. And E, you plug in positive 1.1. So that is delta G naught. in joules, okay? By default, they're all in joules. So you report the answer in kilojoules. So if I plug in the calculator here, okay, a sec. Let me go to my calculator. So 2 times 96485 times 1.1. So it would be negative 212,267 joules. So usually we would like to report as negative. So that would be kilojoules per mole of reaction. So you can see the delta G naught is negative, suggesting that the reaction is spontaneous because E is positive. If I want to find out the equilibrium constant, I can use delta G or E. If I use E, this would be positive RT over NF, natural log of equilibrium constant. Yeah. So I can use this equation to find it. And once again, I just plug it in. E is positive 1.1. Okay. R is 8.314 because we're dealing with energies. And temperature is 298 Kelvin, standard temperature. Molar electron transfer is 2. Faraday's constant, 96485 again. And then natural log of equilibrium constant. So you got to divide it over and E, which is anti-natural log on both sides. So let's do that. Yeah, you're going to get a big number because you're spontaneous. K will be large, right? Huge. So 1.1. So 85.7. So 85.7 of, so you E both sides. So equilibrium constant is going to be huge. Is E to the power of 85.7. That is very, very large. So again, large K means this reaction essentially goes to completion. It's so spontaneous that equilibrium constant is huge. There's no point of talking about equilibrium constant. So just from the E, okay, we can, if you know E, you can find the other two. All right, so, and how do you find the E? From the reduction tables I showed you earlier, yeah? So the E values are here on the reduction table. You gotta find your own redox reactions here, okay? All right, so let's go back to our chart. Again, we're on galvanic cell. You have to know how to label these, yeah? So again, oxidation occurs on anode, reduction occurs on cathode. Electron flow in the wires from anode to cathode, period. Salt bridge prevent charges from buildup. Cation, potassium ion flow to the cathode, anion go to the anode. You need it. If you remove the salt bridge, the battery will stop. So the E will drop to 0 right away. There's no, the voltmeter will measure 0 if you pull the salt bridge away. So we said the voltmeter measure delta E, not delta E naught, and it decreases, right? Delta E will decrease over time because Q will always increase over time for spontaneous reaction. As Q goes larger, delta E decreases from 1.1, eventually at equilibrium, delta E equal to 0, and you ended up with this equation. Okay, we're almost there, yeah? Next thing I said here, I'm gonna label here, I said anode loses mass here because zinc is dissolved as it oxidizes, and cathode gains mass. Now that is not always true. So I'm going to say in general, okay, that's not always true though, yeah? It depends on the reaction, okay? Anode loses mass. And cathode gains mass, yeah? So, but it's not always true, in general only, yeah? So it depends on the reaction, look for the reaction, yeah? Okay, if you have two metals, anode is always the more reactive metal because you are looking at a single displacement. So given if two metals are involved, are used, anode is always the more reactive metal, period. Anode is the more reactive metal. And cathode is the less reactive. So zinc and copper 2+, isn't this single displacement? This is single displacement, okay? And zinc is reactive enough to displace copper. So zinc is more reactive than copper. It displaces copper 2+ from the solution because zinc is more reactive than copper. So that is also something take away from these reactions. Okay, and one last thing here. Initially, Q has to equal to 1. This means that I would have to have zinc 2 plus concentration initially equal to 1. Even though I don't need zinc, I need to have 1 molar on this left beaker. And same thing with my copper 2 plus on the right side, it has to be 1 molar as well, because that is required by the standard conditions, yeah? So initially, both zinc 2 plus and copper 2 plus is 1, so Q is equal to 1. But then as reaction proceeds spontaneously, Q increases over time as Q becomes equilibrium constant, okay? All right, so those are the items I'm gonna put it here, okay? So let's look at how this is applied to our test, okay? And see how this can be applied to the test. So let's go back to our test. So the test here, you're given this is your battery, yeah? You can see the voltmeter is on the top, which is measures delta E. And you can see the wires. And I told you electron always go from anode to cathode. So right away, you know who's the anode, who's the cathode, right? So the metal here must be the anode, and here must be the cathode. Oxidation must occur on the anode. Reduction must occur on the cathode. The electrolyte paste in between is the salt bridge. So salt bridge is a paste. It's just that I use a U tube. This one is not a U-shaped tube. So that is the salt bridge. So if I have a cation, K plus, which way will it go? Cation will go to cathode. It's gonna migrate to the cathode. An anion, let's say I have a hydroxide, it's gonna go to the anode, which is the oxidation side, period, right? Well, depends what you put in here. If I put nitrate, that will go to the left side, right? Anion go to the anode. So it just depends what you put into the salt bridge, okay? So I want to show you the similarity, all right? And then more, this voltmeter is measuring delta E. Delta E naught minus RT over NF ln Q, okay? So this voltmeter will initially measure delta E naught. Let me erase this one, yeah? But then as time progresses, what happens? Q will always get larger, so this will go down until delta E becomes 0 at equilibrium when the battery is flat, okay? And at that point, Q becomes equilibrium constant. So I'm repeating what I'm saying using a different setup. The switch now is on, you can turn it off, then there's no more voltage. Voltage drop to 0 if you turn on the switch. Sorry, right now the switch is on. To turn the switch off, it actually looks like this. So that means the battery is not working. Okay? Only got to put it down, yeah? So the circuit is complete. Off is like that, okay? When it's flipped open, it's off. Okay, so what about this? And they even tell you which one is anode and cathode. They don't have to tell you. So what we're doing here is this. We're doing a battery. And this is a type of battery. It's called metal air cells. So metal is the anode, air is the cathode. There's a new type of portable energy consists of metal anode. And you also have alkaline electrolyte paste. That would be the salt bridge. That has water, porous cathode membrane that lets oxygen in. Okay, so when they say that they want to let in the oxygen from the air, okay, what is the purpose of letting in the oxygen? Well, probably because oxygen is one of the reactants, right? Okay, you need oxygen. Okay, so this is the reduction. Reduction needs oxygen, yeah? Oxygen will become reduced. And then here's the table. So you see, they won't give you the entire table. They'll give you this. So here is the reduction of oxygen right here. Again, they will always give you reduction. They will never give you oxidations, yeah? So these tables are by default given as reductions. And I have all reductions, okay? So let me take a picture of this and I wanna label them. And you can see that there's 3 different metals are involved here as well. So look at the 3 different metals. What are the 3 different metals? I have zinc, I have sodium, I have calcium. So those are the 3 different metals. So 3 possible metal anode. So those metal right here, I can put zinc here, I can put sodium here, I can put calcium here. But I have to flip these if I want to do that. Because anode is oxidation. So I gotta flip all these reductions, right? So I gotta flip them. So my only reduction is the first one, my reduction of oxygen, and when oxygen is reduced, you can see it becomes hydroxide. So there's one reduction right here, that's the only reduction, okay? So this reaction, oxygen is let in because you need it. You're actually reducing oxygen using electrons and turns into hydroxide, yeah? So that is your reduction. Right here, you're told this equation. Do you have to come up with this one? No, you're given right here on the table. And the three oxidations are implied is one of those three. Either zinc is oxidized, so I gotta flip this, or sodium is oxidized, then I gotta flip the second one, and what a calcium, right? We don't know which one. If I want a zinc one, then I will write zinc plus 2 OH minus, and that's an oxidation because I flipped it. You'll get zinc oxide, and you're gonna get water, and you're going to get 2 electrons. So that will be the oxidation reaction. So I'll be using zinc here. And oxygen is let in from the air. So this is my redox reaction. Do you see I have electron transfer here? How many electrons are transferred? I have 2 from oxidation. I have 4 from the reduction. So the number of electron transfer between 2 and 4 is 4. So N is equal to 4. 4 moles of electrons are transferred. If I use a zinc metal as the anode, and I use oxygen as the cathode. 2 electrons produced by zinc, 4 electrons used to reduce oxygen, N is equal to 4. Does that make sense? Yeah, okay. So by telling us which metal to use, they can tell you the oxidation half and reduction half. If I have the oxidation and reduction half, then I can write the overall balanced equation, just the same way as I did with copper and zinc, okay? So let me take a picture of this and we'll continue, yeah? So this one. So electrochem is not very, very difficult, guys. Once you understand electrochem, it's actually quite easy, yeah? Okay, so you need to memorize that chart that I gave you, the chart of that galvanic cell, because there's another chart which is for electrolytic cell. So let me, I want the whole picture, I guess. Yeah, let's just take the whole picture. Give me a sec. So let me take a picture. This takes forever because of lagging. I don't know why it takes forever. Okay, so again, the voltmeter connects them. Wires are connected to voltmeter, so you can measure the delta E, which will always decrease until it's 0. Okay. And you need a salt bridge, which is electrolyte paste. So here is my my question, yeah? Okay, so let's take a look at this for a sec. So let's put this here, okay, and see how important this is, yeah? Okay, so if I use the zinc, if I'm using zinc as the metal, yeah, then I would know which equation to flip. So all the question have to tell me is which metal are we using, okay? So I'm going to assume that the question tells you to use zinc right here. I want to use this one. So this would be, I have to flip this one. That would be my oxidation. And my only reduction here is oxygen, right? All the other one does not have oxygen. So this must be why oxygen is used here. So let me write down I flip this one. I will get zinc plus 2 OH minus. Again, this is not something you memorize. They're given to you. You just have to pick an equation and flip the right one, like Hess's law. And zinc oxide, water, and 2 electrons. So here, water and 2 electrons. This is oxidation, so this is your anode. And I'm going to write the reduction on the bottom so we can add the half reaction together and balance it. So the reduction, again, you don't memorize this, you have them right here, you're given that. So it's oxygen plus 2 water plus 4 electron, and that will produce 4 OH minuses. And I'm going to carry the E value here. So the oxidation now become positive 1.31 volts because I flipped it. The reduction remained at positive 0.34 volts. Do you see how I got those values, right? Okay, I got to flip the oxidation one, yeah? And to balance this, how do I get rid of the electrons? Don't I have to multiply the first equation by 2? Because 2 electron and 4 electron will not cancel otherwise. So you got to times this by 2. Is there any questions on that? Yeah? Okay. And when you times the equation by 2, E does not change. We talked about this last week. If you times 2 divided by 2, E remains the same value. Okay, but I'm going to multiply that by 2 and show you what happens. Can you see what happens when I multiply this by 2? Okay, in blue, I will have 2 zinc, but 4 hydroxide will cancel. They're going to be gone. Yeah? And 2 times water, the 2 water will cancel the 2 water here. So there's no more water. And the 4 electron will cancel 4 electrons. So what is left is actually 2 zinc solid plus oxygen. That's it. And you're going to get zinc oxide times by 2, which is also solid. Ionic compounds are solid. Zinc is a metal, oxygen non-metal is ionic compound. That is my overall reaction, and my cell potential will be the sum of those, right? So that's 1.65. So it's positive 1.65 volts. I just found out the delta E for this reaction. It is spontaneous, of course. If I know this, I can find delta G. I can find out equilibrium constant if we want, right? We already did that, okay? So that's the reaction. This is the overall reaction. If I write Q, how do I write the expression for Q? Yeah, you see there's a bunch of solid. Oxygen is not solid, so it'll be 1 over concentration of oxygen. Do you agree? Yeah, if I write Q, right? And if I want to use pressure, then Q will be 1 over the partial pressure of O2. So it depends, you want QC or QP. Same thing with Kc and Kp. Kc is 1 over concentration of oxygen at equilibrium. And Kp is 1 over pressure for oxygen at equilibrium, right? So it depends what you want. Okay, you can use concentration or pressure, okay? So this is a produced great, right? That is if I use zinc. What if I use another metal? What if I use, I wonder which one would be better, right? What if I use sodium metal as the anode? Would that produce more electricity? Yes or no, guys? Okay. See, if you use the sodium metal, then you got to flip this one. And that means your oxidation will be positive 1.60 volts, and your reduction is still positive 0.34 volts, right? So your cell potential using sodium is 1.94 volts. So it looks like it's better, right? Okay, so you can do these kind of analysis. That's what this is. They give you 3 possible metal, and we don't know which one to use, but we know for sure the reduction has to be the one involving oxygen. That is the only equation that has oxygen in them. Okay, so that's what this is. Yeah. All right. So let's look at the next question, see what they want. Okay. So we didn't even look at the question yet, but we already answered a lot of it. So if you look at this one here, early forms of metal air cell use zinc, which is what we did, right? And zinc oxide is produced. Sure. Isn't this the overall reaction that we did? Yeah. So do we need to do this ourselves? No, they give you the overall reaction. Again, I'm going to show you side by side. The overall reaction is given. It is 2 zinc metal plus oxygen give you this. So they give it to you without telling you how they got it, but this is how they got it. They literally flip to get the oxidation and reduction that balanced it. And we know the E already. So the question is, what is number 1? Use the data in the table, calculate the cell potential. What is cell potential? That's E. Okay, so this is the answer right here. 1.65 is the answer. Okay, so if we didn't do this, all we have to do is go back to the diagram and we just flip the one that is zinc. Flip the zinc, keep the oxygen as is. Add them 1.65. Okay. That will be the answer, right? And then number 2, the electrolyte paste contains hydroxide. That's an anion. It's going to flow to the anode. The electrolyte paste is the salt bridge. Draw an arrow in the direction of the migrating OH minuses as the cell operates. So you just have to draw hydroxide going to the left. That's it. So your answer is just a drawing, OH minus, anion go to anode. That's it. Now you get the point. Yeah. So that's the answer. Okay. All right. So 1 and 2, we're done. Okay. Next one. We're going to look at part B now. So, okay. B. So what do we do with part B? So B says we're using hearing aid. So a fresh zinc air cell is weighed on a balance before used as a hearing aid. As the cell operates, does the mass of the cell increase, decrease, or remain the same? So we're doing part B. So this is the overall reaction that we're given. Again, you don't need to write this down. You're given this. Okay. So if you look at this is the cell. Again, this is the overall reaction. Can you tell just by looking at the reactant and the products? This entire thing is this is the cell. Okay. This is the entire cell. Is the cell's mass? This is before, and this is after using cell as a hearing aid. Do I lose or gain mass? That's all they want, right? And by looking at this, I am gaining oxygen from the air as I produce zinc oxide. Before, you only have zinc metal. And the reaction grabs oxygen from the air and you're producing zinc oxide. Wouldn't that mean gain mass? So after using cell gains oxygen from air and mass increases. So this means mass increases. So that is the answer. Okay, as you operate, the mass of the cell will increase because it's gaining oxygen. How do you justify that? Because chemistry wants to justify. So you see, they give you a clue. Justify your answer from B1, which is the overall reaction, right? So from B1, I'm looking at B1. Oxygen is gained from the air, and then it gets incorporated into zinc metal. So the total mass will increase. Okay, because the cell is put on a balance. Okay, the balance cannot weigh air, right? It weighs zinc. But now you're weighing oxygen as well, as oxygen turns into zinc oxide. That's it. That's part B. Yeah. And part C, now you take the zinc air cell to top of the mountain where air pressure is lower. So you're no longer at standard conditions, because what is the standard condition, guys? Okay. The standard condition is when Q equals to 1. So if your Q is 1 over pressure for oxygen, yeah, and now you're at the top of the mountain. So this is at sea level, yeah, because pressure for oxygen is 1, okay, a standard condition. Now at top of the mountain, the pressure of oxygen is not 1, it's less, okay? So how is that going to affect the cell potential? So now you have to show them right here. This is C1, right? So at top of the mountain, the partial pressure of oxygen drops as air becomes thinner, right? Okay, decreases. So Q increases, right? So Q becomes larger. And what does that have to do with cell potential? They want the Nernst equation. You write down the Nernst equation, which is this one, right? Minus RT over NF ln Q. Then you look at this mathematically, right? What happens when Q increases in value? Well, delta E will have to go down, yeah? So your cell potential, if you take it to the top of the mountain, will be less than, okay, at the sea level. And at the sea level, we already calculated, it was this delta E naught. What was the delta E naught? We calculated to be, what was it? 1.65 right here, yeah? It was 1.65. So we calculate this to be 1.65 volts. But this is only true at standard conditions, when Q equal to 1. But now on top of the mountain, your Q is bigger because pressure for oxygen is less. Q is larger, so your delta E will be maybe 1.4, maybe 1.3, right? But it's not going to be 1.65, okay? So your answer is this, it decreases, yeah? And your explanation is what we said. At the top of the mountain, there's less oxygen, pressure of oxygen drops. This causes Q, the reaction quotient, to increase. And according to Nernst equation, the larger the Q, the smaller the delta E, which is the cell potential, okay? And justify your answer by using the overall reaction and the information above. Yeah, why are we using the overall reaction? Overall reaction is how I got Q. So this is from the overall reaction. I got Q equal to 1 over pressure for oxygen, right? Because you cannot include solid. So I'm using that, right? Okay, so that's it. That'll be that one, yeah? Okay, and let's look at part D, another metal air cell. So now let's talk about lightweight. You want this battery to be as light as possible. You don't want to be a heavy one carrying them around. You want to be lightweight. In order to transfer more electron with a smaller mass, we're investigating sodium and calcium as potential candidates for the anode. So the question says, I have 1 gram anode of which metal will transfer more electron? Would 1 gram of sodium transfer more electron than 1 gram of calcium, right? We're not looking at zinc anymore. We're looking at sodium and calcium. Okay, so assuming that anode is totally consumed, so you react to completion and justify with your calculation. So you got to calculate it. So this should bring you to that table for sodium and calcium. That should be what the whole point of this question is, yeah? So I'm going to paste that table out again. And you can see from the table, I'm gonna zoom in and focus on calcium and sodium. Yeah, I don't care about zinc anymore. Okay, so let's see if this will let me move. Okay, okay, it's not letting me move. I don't know why. Let me just delete it then. Here, further away. All right. So right here, again, I'm not going to focus on sodium and calcium. That's what we're comparing. So if you can, and focus on sodium and calcium. What do? Right? I want to see 1 gram of which metal. So I'm focusing on these two. Will produce more electron. Wouldn't I just look at sodium and electron, calcium and electron? This is stoichiometry. Okay. So technically I got to flip them, but I don't need to write it down. I have 1 gram. So I'm going to write it. This is your answer here. You have 1 grams of sodium. You got to use mole ratio to find out how many moles of electron. Which one transfer more electron, right? So grams of sodium to moles of sodium, that is molar mass about 22.99. So don't round it, yeah? And then 1 mole or 2 mole of sodium, I'm sorry, right? If you look at the balance equation, wouldn't that produce 2 moles of electron? So there, this is how many moles of electron that can be created, yeah? And then I do the same to compare. Now I use calcium, right? Calcium has different molar mass. Molar mass is 40, okay, don't round it, 40.1 or something, yeah, 40.01. So you get calcium. And then the ratio is different. The mole ratio from calcium to electron is 1 to 2. So 1 mole of calcium on the bottom to 2 moles of electron. So that will be moles of electron transferred if I use calcium. So I just have to compare those numbers. Now, question is, how many sig fig do I carry this out to? They probably won't mark it off for sig fig anyways. So it's irrelevant. There's not enough points for sig fig. But if you insist, I think it's 2. I didn't use it. I think they say 1.0 gram, right? Yeah, do you see that? 1.0 gram. So 2 sig fig question if you must, yeah? So I probably should have written 1.0, 1.0, and carry my answer to the proper sig fig. It really doesn't matter. You're not going to get points for this, okay? Sig fig. So 1 over 23 is 0.043. And this one is 2 over 40, right? So that's 0.05. So 0.050. So which one is better? If you were to buy this, you want to buy calcium because 1 gram of both, and the lightweight is what we care about, not the cost. Maybe calcium is cheaper than sodium, don't know. But in terms of mass, lightweight application, 1 gram of calcium produce more electron than 1 gram of sodium. So that's the one you want, yeah? Okay, so let's go back to the question one more time. The question is again, okay, is asking us which electrode transfer more electron for 1 gram. So the answer is calcium. Your justification is that stoichiometry, you put it down, yeah? And that is it, okay? Part E has nothing to do with electrochem. It has to do with electron configuration, yeah? So what is the electron configuration for zinc? We already did it in the ground state. So that would be argon, 4s2, 3d10. And which sublevels are electron removed when it's oxidized? Well, the valence electron. So which sublevel? A lot of people write down 4. That is wrong. 4 is the energy level. That's not the sublevel. Sublevel is S, P, D, F. So don't put 4. You can put 4S or S, but you cannot just put 4. So when they say sublevel, it is not energy level. Sublevel is S, P, D, F sublevels. So either you say 4S or S. You cannot say 4. 4 is not a sublevel. 4 is the energy, principal energy level. So watch out for that, please. Yeah. Okay. These 4s electrons are the ones that travel in the wires all the way to the cathode and that reduced oxygen. Yeah. Okay. So that's what these are. Does that make sense? Alrighty. Now that is electrochem. Most likely you'll get this. Now there's another type of electrochem, which is what if you are non-spontaneous? Okay. So that would be called the electrolytic cell. So let me go over that. Electrolytic cell diagram, you need to memorize it. Okay, I'm just going to go over it right now instead of moving on to other tests. Okay, so I will write down the differences between them, but you need to memorize this. Okay, so this is the electrolysis or electrolytic cell. These are not spontaneous. So your E must be negative, your G must be positive, and your equilibrium constant is small, less than 1. So electrolytic cell, you need a battery, like an external power supply. So this is in the galvanic. You need a power supply. They call this external battery because the power supply is the amount of electricity that must be provided to drive this non-spontaneous reaction, right? So we are using electricity to drive, to push, to drive a non-spontaneous reaction, to make a non-spontaneous reaction spontaneous, yeah? So that is the whole point, okay? And also, there's no salt bridge. You're not going to see a salt bridge. There's no need for salt bridge. And also, there's no voltmeter because you're not producing electricity. So you're not going to see those. What you have is a power supply. Now, a lot of the stuff still remain the same. Okay, so we need an example. So let's look at the most famous electrolysis, which is the electrolysis of water. Water can oxidize. Water can also reduce. I went over this last time to prep for this. Yeah. So the oxidation of water, you get oxygen. The reduction of water, you get hydrogen. Period. Because hydrogen cannot be oxidized. Hydrogen is already 1+, so hydrogen has to be reduced. So you're going to get hydrogen gas. So if you oxidize water, you get oxygen gas. Okay. So this is the oxidation reduction of water. It is non-spontaneous, yeah? So you can also add them together, you get the overall reaction. The overall reaction is water becomes O2 and H2. And you can get the overall balanced equation simply by putting a 2 here and 2 here. This is gas, and water is liquid. This is the overall reaction. I don't have to do the half reaction to get to this one. But if I want to find a delta E, I need to use delta E, yeah? Okay, so like that. So again, you don't need this. You will be given the half reactions. So you just have to find them. So let me find them for us, yeah? So right here, this is the chart that you will not be given. So I'm going to go to this chart and then fish out the one that we need, okay? So I am going to give you this one. Okay. Can you tell me by looking at this, if this is the one right here, is this the oxidation of water or does this have to do with the reduction of water? One of them is wrong. Okay. Does this have to do with, I know this is written as a reduction because they always are written as a reduction. But my question is, this reaction written, I highlighted here, does this have to do with oxidation or reduction of water? Okay, now it's here. Okay, right here. Okay, I'm gonna write this. Okay. Okay, so this will be what you give it. This actually has to do with oxidation of water because there's no hydrogen. So it's nothing to do with reduction. This is the equation you have to use for the oxidation of water, but I have to flip it because oxidation of water produce oxygen. Oxygen is product. Okay, you see that? So this equation here has to do with oxidation of water, not the reduction. Reduction of water involves hydrogen. There's no hydrogen here. But this is reduction, so I gotta flip this one. And you get 2 water on the left side, and you get oxygen, 4 H pluses, and 4 electrons. And the E value is negative 1.23, meaning that water does not spontaneously become oxygen, right? We know that. We have a bunch of water. Otherwise, you lose water forever. Okay. What about the reduction of hydrogen? So I'm going to give you one, okay? So reduction of hydrogen in the basic medium is a little bit harder. So sometimes it's not given. Oh, good Lord. So I don't think we're given this. Yeah, we're given right here. So this equation has to do with the reduction of water because look, hydrogen is involved. Hydrogen is involved, not oxygen. So this is the reduction of water. Okay, so we need to be able to fish out. So when they give it to you, you got to use some common sense. Which one is which? And this reduction, I don't need to flip anything because it is already reduction, right? They will always present the equation to you in the form of reduction. Yeah. So do I need to know how to balance this myself? No, it's a balance for you. It's 2 water plus 2 electron produces H2 and 2 OH minuses. The E value is negative 0.83 volts. So we know that is not spontaneous also. And now I want to balance the equation. I have 4 electrons on the right, 2 electrons on the left. Don't I have to multiply the bottom by 2? Yeah, I need to do that. But E will remain the same. So the delta E, I'm just going to add them. The answer is negative 2.06 volts. So the electrolysis of water is non-spontaneous. It does not occur. Okay? And you can literally prove by doubling the reduction, and you'll see water canceling out, and everything will become the overall. Okay? So if I want to do this using electrolysis, what is the setup? What does the setup look like? That's my whole point here. Okay, you still need to have anode and cathode. So right away, anode is still where oxidation occurs. Anode is oxidation. That does not change. Cathode is where reduction occurs. That does not change. Okay. So, okay, and there's no voltage, and you need a power supply. So here's my power supply. I'm going to draw the power supply like a battery, like a car battery. Yeah. So I'm even trying to draw this with 3D. Yeah, car battery. You've never touched a car battery before. That's okay. You have the anode and cathode. They look like a piece of metal here, stuck out like that. It's a car battery, yeah? So the anode is red and is positively charged. Anode is red, okay? So maybe I should have used red, okay? So the red wire is the terminal, and cathode is the black one, which is black. So you need to connect wires to anode and cathode, yeah? So I'd have to strap it using alligator clip. And then I have to do electrolysis. So electrolysis does not need a soap bridge. So why don't I use, I'm gonna actually connect them into 2 separate test tubes. So here are the test tubes. So this test tube, I'm gonna invert it because I'm collecting gases, right? Oxygen is a gas, so is hydrogen. And this one, I'm gonna connect to a gas inverter test tube too, because I'm collecting gases, so I wanna invert them. So this is where oxidation will take place. This is where reduction will take place. What is my raw material here? Water. Electrolysis of water requires water. And you are going to produce oxygen and hydrogen, yeah? Do you see the coefficient for hydrogen and oxygen is 1 to 2, oxygen to hydrogen? You are literally going to get twice as much hydrogen for every part of water. Does that make sense? Because the balance coefficient is 1 oxygen, 2 hydrogen. So I'm going to get twice the amount of hydrogen. And then again, oxidation produces oxygen and reduction produces hydrogen. This is my water, okay? And you'll see literally bubbles of water here. Bubble, 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 bubble. This will be oxygen collected here, and bubbles are coming out here, and this will be hydrogen collected in here. Okay, electrolysis. Again, oxidation of water produces oxygen. So what's happening on the anode? Water is being forced. It doesn't want to do it. It's forced to oxidize. Okay, so you force water to give up electron. Okay, so you produce oxygen. So what's going to happen is that the battery literally is pulling electrons. It's pulling electron from water. So the electron that travel in the wire from water, okay, will now go through the battery and it's going to go to the cathode, okay? So we are using the external power supply to pull electron from water. So the power supply forces water to oxidize on the anode. So the power supply, it forces water to oxidize at anode. And those electrons, and it pulls electrons towards the cathode. And then it's going to force feed electrons to the water at the cathode. So the water at the cathode do not like electron, but they have no choice. I'm forcing electron onto here. So it's forced to reduce. Okay, that's the reduction. So water is forced to reduce, to gain electron at cathode because of the power supply. So that's how you force water to become oxygen and hydrogen using the power supply. Okay, again, I get twice as much hydrogen produced than the amount of oxygen because the balanced coefficient, right? There's just more, it doesn't work. There's just more hydrogen than oxygen, okay? Twice as much hydrogen. So that's the electrolysis. So what is similar is that electrons still flow from anode to cathode, just like galvanic cell. And that happens in the wire, okay? Like this, okay? So let's look at some example. Okay, so some example would be, okay, some application. One of the most common application for electrolysis is actually to use, we're actually using something called electroplating. Electroplating is to plate metal, yeah? Metals, like a silverware, the cheap one, not real silver, to plate metals onto another metal, yeah? Another object or something, yeah? So we can use electrolysis, something called electroplating. So for example, I can do this. Let's say you can do this at home. You have an iron spoon, right? The spoon is not made from silver and you're not happy with it. So this is an iron spoon. So I want to coat it with silver. So I need to dip this into silver. And I want to make sure that reduction would occur. So the iron spoon is going to be covered by a thin layer, uniformly coated silver metal. So you get your silverware, right? So you want the silver to reduce onto iron spoon, yeah? So silver deposit will show. So you have an iron spoon here. So do you want this to be your anode or do you want this to be the cathode? Well, the answer is that this is reduction. I want silver ion to reduce. So if this is reduction of silver ion into silver metal, this has to be the cathode because cathode is where reduction occurs, red cathode. So I would have to strap my iron spoon to the cathode of the battery. Cathode of the battery is black anode is red, yeah? So this is your car battery again, okay? So what does the car battery do? It's going to have oxidation. We don't know who is gonna be oxidized, but you need to provide an oxidation, which will force electron, the battery will force electron out of oxidation, and those electrons will travel in the wires, and it's gonna reach your metal spoon. And those electrons gonna force itself onto silver, okay? If you want gold, put gold ion here. If you want copper, put copper 2+ ions, right? Just whatever metal you want. That's called electroplating, okay? So let's look at a calculation involving electroplating. So the question is, if, okay, 2 ampere, that's current, okay, is used for, let's say 15 minutes. My question is, okay, then how many grams of silver it can be deposited on my spoon? Okay. So how do you do a question like that? It's super, super easy. Okay. You need 3 things. 1, you need the current, which we do. Second, you need balanced half equation, which is right here, we do. And the third, you need Faraday's constant. That's it. So let me write down those 3 things that we need. Okay. So to do these kind of questions, we need 3 things, 3 items. That's it. Always 3 things. Don't memorize formula. Some teachers use formula. This is common sense. Use 3 things. Number 1, I need the current. And current is measured in amperes, right? Amps. How many amps? How many coulomb per second, right? Number 2 I need is the half reaction, which is the reduction of silver. And the third is Faraday's constant, which you memorize. 96485 coulombs of charge is carried by 1 mole of electron. You need those 3 things and you can answer the question, yeah? Okay, so here is how you can apply it. So the question is, if I use 2 amps, that's 2 coulombs every single second. That's right, per second for 15, first of all, 15 minutes. Seconds, I just times 60, right? So 1 minute is 60 seconds. Okay, then I use the current. 2 coulomb per second. Do you see seconds cancel? So this is the current, okay? You need that. That's the first thing you need. Now you have coulombs. So if I stop here, this is how many coulombs are delivered in 15 minutes by 2 amperes of current. 15 times 60 is 900 times 2 is 1800. So this shows you that in 15 minutes, 1800 coulomb is delivered to your iron spoon. But we don't want to stop here. We continue. The only conversion that you have with coulomb is Faraday's constant. So you have to use Faraday's constant, converting coulombs to mole of electron. 96485 coulomb is 1 mole of electron. So this is why you need Faraday's constant. So if you stop here, instead of how much charge is delivered, this is how many moles of electron delivered. In 15 minutes, using 2 amperes, you have delivered this number of moles of electron to your iron spoon. So we need one more thing, which is the half reaction. The half reaction shows the coefficient. Whoops, I used black. So what is the moles of electron? To silver. Moles of Ag, and that's 1 to 1, right? Your half reaction is 1 to 1. 1 mole of electron to 1 mole of ion to 1 mole of silver, right? 1 to 1 to 1 mole, okay? That's the 1 to 1 ratio. Does that make sense? Okay. It's lagging. Okay. So it's 1 to 1 to 1 ratio, okay? 1 mole of silver metal requires 1 mole of electron. So let me go back. So this is from the balanced half reactions. You only need those 3 things. That's it. If you know, now you have moles of silver deposited. They're 1 gram. So 1 mole of silver is molar mass, 143.5 grams, something like that. Okay. So that would be the answer. You see that? So what do you need? You just need 3 things: the current, which will be given, and Faraday's constant, and your half reaction. You can do any kind of question that involves electrolysis. And those are the electrolysis questions that you'll be asking. Let me do this another way. Okay, I'm going to reverse the whole thing. So here's the question. How long would it take to deposit, let's say I have 4 grams of, I'm going to use gold, yeah, AU, using what? I'm going to change 0.5 ampere. Okay, so that would be my question now. How long will it take to deposit gold, 4 grams of gold, okay, using 0.5 amperes? So again, I need 3 things. I need the current, which is 0.5. I do have that, right? I need Faraday's constant, which is 96485 coulombs per mole. And I need one more thing. I need the half reaction. So you get those 3 things, you get the answer. What is my half reaction for gold? Gold, you should know, is 3 plus. So you need 3 moles of electrons to reduce to gold metal. That's my half reaction, yeah? So how do I start? I start with grams. I want 4 grams. So you have 4 grams of gold. You convert grams to moles of gold. From moles of gold, the only thing you can convert from moles of gold is to moles of electrons. For moles of electron, you use Faraday's constant to convert to coulombs. From coulombs, you use current to convert to second. So there. 1 mole of gold is 197 grams, that's the molar mass. And this is the half reaction. The half reaction says 1 mole of gold requires 3 moles of electron. Next one is Faraday's constant. 96485 coulombs is carried by 1 mole of electron. So you can convert from moles of electron to coulomb. So this is how much coulomb you need. And the last conversion is current. It is 0.5 amperes. So that would be 0.5 coulombs per second, right? That's what 0.5 amperes mean, coulombs per second. So you can see your final answer will be in seconds, which is how long it would take. So this question we just did is exactly the reverse of the one we did previously. Previously, I start with time, I get grams. Now I start with grams, I go backwards, everything is reversed, I get time. Okay, these are reverse of each other. Okay, and again, you need the same 3 things: half reaction, okay, the balanced half reaction, Faraday's constant, and current. Okay, all right, that's the end of the electrolysis. Yeah, so there's some other things that you may need to know. So we'll see when they come up. Okay, all right. That was question number 1. Okay, again, we're not going to finish the test, but let's see. Let's look at question number 2. Okay, if you look at question number 2, you can see right away I see delta H is positive. Yeah, if you haven't, whoops, sorry, I took out the. Okay, so you guys are still there, right? Okay, so here we have this one right here. So we have this is a setup. You can see the setup's collecting a gas over here. So the bubble, and you collect the gas here. So gas 1, PV equals an RT. You can find out how many moles collected. And you're heating up something with a catalyst, so you'll speed up the reaction, yeah? So ethanol is being heated, and the gas travels in here and collected over here. So that's a very simple setup, okay, to collect a gas product. And the reaction is given here. You can see right here, right? So ethanol is decomposed, and you get this, which is the gas, and also water vapor. So do you see this ethane here collected? Will also include a bunch of water, yeah? So the pressure of ethene plus the pressure of water is the total pressure in the container, yeah? Okay, so I'm lagging quite a bit. Okay, and by the way, you can also see delta H is positive, is endothermic, as with decompositions are. And if you produce a bunch of gases, entropy is positive. So I have positive, this is scenario number 3, right? Endothermic reaction that produce more disorder. This is spontaneous at higher temperature. That's why you heat it to make it more spontaneous, yeah? So you can see thermodynamics at play, okay? So right away you can kind of tell, even without reading, this is thermodynamics and this is PV equals to RT kind of question, yeah? All right? Okay, so here is the question here, yeah? I think, let me try to take a picture. I don't know if this is a good idea to take a picture here, okay? Let's say we have this equation. All right. So the first one is stoichiometry. I'm looking at this as stoichiometry or PV equals to RT, something like that, right? So let's look at more closely. I haven't read the question yet, but let's go back to our notes. So we're on question number 2. Again, 1, 2, and 3 are those long questions you want to be very good at, right? No matter how they tweak it, they will combine multiple concepts together as much as they can, okay? And then you just have to know how they're all related. Okay, so this is, oh, good Lord. Okay, again, I got to delete this. I'm going to move this a little bit over. So let me put that in there. Okay. Now, if you actually measure the conditions for the test tube, you can use PV equals to RT. So here's the question, yeah? The student added 0.2 grams of ethanol. So that is your starting point. You have 0.2 grams, okay? And you use that setup. And then, of course, you produce the 2 gases will be collected. And then it says the volume of the gas collected is this, at this pressure, at this temperature. And the vapor pressure of water is this, okay? So there's 2 ways, A1 and A2, to talk about the moles of C2H4. Okay, I'm going to draw that test tube again. In the test tube, there's C2H4. There's also water vapor. Okay, right here. So if you're looking for how much C2H4 are actually produced, you have to go after the container. So A1 actual produced is from the container. You cannot start with 0.2 grams of ethanol. 0.2 grams of ethanol would be A2. When you try to do A2, you start with 0.2 grams of ethanol. And you look for, in theory, how many grams, how many moles, we're not looking for grams, how many moles of ethane will be produced, in theory. So let's do A2 first, because in theory, if I start with 0.2 grams, I convert grams into moles of ethanol, and ethanol has a molar mass of 46. Yeah, you just add it up. So C2H5OH, and the molar mass is 46. And then the ratio is 1:1 from the balance equation. So 1 mole of ethanol will produce 1 mole of C2H4. That's the answer. That is how many moles you'll produce in theory if you decompose ethanol to completion. And the 3 significant figures here means I have to report 0.00435. That's how many moles of C2H4 is produced in theory. How much do you actually get? Then you got to use PV equals to RT. That's why we go after the container, yeah? So how much do you actually get? I have to first take out water. This point A22 includes water, yeah? That is the total pressure. You always have to take out water. There's always water that interferes with your gas. Okay, so how do we do that? You get a point for showing work, so you have to do that, okay? So water, the vapor pressure we're told in the parentheses is 35.7. I'm waiting for the lag to disappear. So 35.7, okay? That's water. But I need to do that in ATM. So 35.7 to show work divided by 760. That would be the pressure of water in ATM. So I want to give the proper decimal, 3 decimal, yeah? 35.7 divided by 760. So 0.0470. 0.0470 ATM. So now I can plug it in, right? The total pressure is 0.822 ATM. The pressure of water is 0.0460 ATM. And you can find out the pressure of C2H4. So if you solve for C2H4, that is the pressure you need to plug in PV equals nRT. Minus 0.047. So it's 0.775. That is the pressure you plug in PV equals to nRT. Yeah, the pressure is 0.775. The volume you're given 0.0854. You're looking for N, which is moles, and R is 0.0821, and temperature must be in Kelvin. 305 Kelvin. So you find moles, and that's how many moles you actually collected. So divided by R, divided by temperature. So I actually collected 0.00264 moles. So you should have gotten more, right? Because if you we did that in part 2. If we decompose the entire ethanol, we should get 0.00435, but we only got 0.00264. So what is the percent yield, right? That's the next natural question. My percent yield will be how much I actually got, which is 0.00264, divided by how much I should be getting, which is 0.00435. And then you just times 100 to get to percent, yeah? Got lag, so I need to get rid of this. 0.00435, convert that to a percent. So your yield is like 50% or something. 264 divided by 435. So it's 60.7%. That is the percent of yield. So it's not 100%, right? 100% is the second part in black. Okay, but you didn't get 100% of yield, which is perfectly normal, right? So that's A1 and A2, you're done. So this is stoichiometry with PV equals nRT. Not hard, right? Let's look at the next one. So plus, that's the percent yield. Good, we did B already. Now we go into thermal. So the question is, because the dehydration is not observed, so you're not seeing it. Temperature. That the reaction has an equilibrium time. The student saying that it is not spontaneous, and then you have to prove it to him that you do the thermodynamic data, that will be delta H, delta S, and delta G. Does that support the student's claim? So that means you plug in to find delta G. Okay. So in this case, again, let me take a quick picture of this. Okay. You are given delta H and delta S. All you have to do is plug in to find delta G. And remind you here, this is the delta H and delta S, right? They're both positive, right? So let's see what would happen if I do that. Okay, so maybe not, doesn't like it. So let me put it back here. So we're doing the next part now. Okay, so here it is. We are solving for delta G. How do I do that? With delta H and delta S, you do delta G equals to delta H minus T delta S. It's that easy, yeah? Just plug it in. Make sure you put temperature in Kelvin, and your S has to be in kilojoules, because if you look at the S that we're given, it's not kilojoules, it's wrong unit. It's 126 joules. So you're going to divide by 1,000 for 126. And delta H is 45.5 kilojoules. That's fine. Okay. So divide 126 by 1,000. So let me move it back. Okay. So 126 over 1,000. Don't forget to do that. Yeah. That's what you have to plug in. Temperature, we're doing at 298. Don't use 305. That's the whole point right now. We're doing 298. So you cannot use the temperature you used for PV equals RT earlier. And this is, what was this? 35 or 45? 45.5. So let me go back here. This is 45.5. So I'm solving for delta G for the reaction, the standard condition. Yeah. So mathematically, make sure you do not mess up this. This would be horrible if you do. Okay. And this is 45.5 minus the answer. Yeah. So I got 7.95 kilojoules positive, okay, per mole of reaction. So is the reaction spontaneous? Do the thermodynamics support the claim? This is non-spontaneous, right? Because G is positive, so yes, it does support the student's claim that the equilibrium constant is less than 1. Okay, so include justification with G. All right, let's see what the next part is. Okay, so yes, it supports the claim, right? Let's see what the next one is. Next one is part D. Okay, now I think I need to talk a little bit about equilibrium constant because the student is talking about the equilibrium constant. So let me go back. Delta G is not enough. I'm going to say that I have to prove and support the delta G, yes, but I have to connect that to equilibrium constant, right? I haven't done that. So you can just say that since delta G naught is negative RT ln K, and you can plug in equilibrium to find the equilibrium constant and then prove is less than 1. So this is 7.95 kilojoules. So your R must also be in kilojoules. So 8.314 gotta divide by 1,000. Don't forget that. And temperature is 298 and natural log of K. I want to solve for equilibrium constant and prove it that this is indeed less than 1. Okay, so let's do that. So again, your R is in joules. Because I'm using kilojoules, I divided R by 1,000. So it's 8.314 divided by 1,000. Yeah. So I got e to the negative 3.2, which is indeed less than 1. Okay, so that's my proof. The student's claim included a calculation of delta G, included a calculation of equilibrium constant. So yes, it supports the student's claim, right? Okay, whatever that is, yeah. So so I read it a second time. I decided to go for equilibrium constant because his claim is on equilibrium constant. We just have to use G to show that. All right, and that's it. The next one is no more thermodynamics. It moved right away to Lewis structure, bond angle, hybridization, blah blah blah, right? And intermolecular force. So super easy stuff. Once you are used to these, intermolecular forces are easy. Yeah, you cannot miss intermolecular forces and Lewis structures. Carbon like to have 4 bonds. Oxygen like to have 2. Hydrogen likes only to have 1 bond. So just using that information, you can pretty much draw ethanol. And we have been drawing ethanol for quite a while. Okay, ethanol, carboxylic acid, you need to know how to draw them. So ethanol is 2 carbon alcohol. So make sure we know that, right? And the Lewis structure is super easy. You just have to finish it here. So here, single bond, single bond, single bond, single bond, single bond, single bond, they're all single bond. But there's 2 lone pairs on oxygen to make an octet. So you can see because of this, your carbon is 4 electron domain sp3 hybridized tetrahedral, both of these. Your oxygen has 4 electron domain. It is also sp3 hybridized, but they are bent. The first 2 carbon are tetrahedral, right? So if you really have to draw out the bond angle, this is kind of how you draw it, right? So let me just draw it out, okay? So this would be a wedge means you stick out, dash line means you go in. You don't have to draw it like this. I'm just showing you what that kind of look like, right? Okay, so also like this oxygen is bent, so lone pair. And there's a hydrogen here, wedge out, and this dash line here goes in. So anyways, right? Remember tetrahedral angles are not the same as the bent. This is not 180 here. That oxygen here may look like 180, but that is actually bent. It is 105, 104.5, doesn't matter. It's not 180, right? Likewise, this is not 90 degrees. This is tetrahedral angle, so it's 109.5. So that is 109.5, right? So be careful how to draw these. So the question is E, what is the approximate COH? COH is not 180, it's about 105, okay? You can put anywhere from 104.5 to 109, even 109 approximately. Okay, now part F. Okay, then we're done. This is Lewis structure, yeah? All right. And what about this bond angle on the left side? This is C2H4. You see, C2H4 is actually trigonal planar. Ethene is trigonal planar. I know they draw it like that. It doesn't look like a planar, but your carbon has 3 electron domain sp2 hybridized trigonal planar. That means all the atoms are on the same plane. These are all 120 degrees. So make sure you can draw these fluid structure quickly. Yeah. All right. Part F. During the dehydration, unreacted ethanol passed through the test tube. And this was collected as a gas, but unreacted was not. Okay, so it's talking about intermolecular force. First of all, C2H4 is nonpolar hydrocarbon, right? Hydrocarbons are always nonpolar, so the intermolecular force is London dispersion force. All right, ethanol exhibit hydrogen bonding. So who has stronger intermolecular force will be ethanol. So the stronger the intermolecular force, the more likely you are going to condense as a liquid. This is why ethanol is collected as a liquid, because it has a stronger overall intermolecular force, as hydrogen bond is over London dispersion. And the weak intermolecular force is why C2H4 is a gas, okay? Because it has a weaker intermolecular force than ethanol, yeah? So this is not how you should give your answer, because you got to explain it. So you got to type it out. So you have to say, first of all, identify, right? C2H4 is dispersion, and ethanol has hydrogen bonding. Hydrogen bonding is much stronger intermolecular force than dispersion, okay? And the stronger intermolecular force explains why ethanol was collected as a liquid, and then the weaker dispersion force explains why C2H4 is collected as a gas. Something like this will be fine, okay? All right, so practice doing that. Again, the scoring guide is going to be posted along with the video, because we didn't finish this week, right? All right, let's look at the next one. Question number, what is that? Question number 3 or something? So this is question number 2, yeah? Okay, if you look at question number 3, is acid and base. It is acid and base titration, which again, we got to come back and review acid and base titration. Titration is not easy, but we know this is a titration because I'm looking at a weak base titrated by HCl. So that is a weak base, strong acid titration, okay? And I told you there's only 3 type of titration. 3 titration, 3 BCA. The first titration is strong and strong, so H plus and OH minus will produce water. That's not this one. The second one is a weak acid with a strong base. That's not this one either. You're going to get water and A minus. This one, we're looking at type 3 titration, where you have a weak base and a titrated by a strong acid. They will just combine. This is how you write the titration BCA, yeah? So we are doing type 3 titration, okay? And if you look at how I know, you read the question, it tells you that, yeah, either explicitly or directly what kind of titration is. Okay, so let me see if I can move this now. Yeah, it doesn't let me move. What is stupid? Let me get rid of this, and I gotta move this away. Okay, so you can see the first question. Now they tell you all this about titration, great, but the bottom line is, if you look at part A, you have a weak base with strong acid because you memorized the list of strong acids. And you also know that is a weak base. How do I know that's a weak base? Because I see a negative ion, okay? An N ion, the negative ions are base. So this thing here, that is a base. K plus is neutral. I don't care about any alkali ions. So what's left of it is C6H7O2 minus. All negative ions now on pH 7 is a weak base. And I'm titrating by this strong acid. I don't care about Cl minus. So what is your net ion equation? They simply combine. That's the answer. So HC6H7O2. And that's it. That is the answer for part A. Simply recognizing that this is a weak base, type 3, weak base, strong acid, you just combine them together. That is the answer, yeah? Okay, second one. I didn't even read the question, yeah. But if you look at if you take a minute to read the question a little bit, it's talking about sodium sorbate, potassium sorbate, actually. Okay, the molar mass is given 150, so you don't have to add them. Okay, so you have a stock solution with known concentration. You titrate 45 mils of the solution with 125 mils of HCl using an indicator, which is required, and you give an equilibrium constant for the acid. All right, that's it. So part B, we asked to do part B. A total of that much is required to reach the equivalence point. Every time you have equivalence point, you have to write down moles of the acid must equal to moles of the base. Yeah, the moles of the acid equal to moles of the base. That's the definition of equivalence. So the other way to think about it is IAMAVA, right? Remember that? I gave you this. IAMAVA must equal to IBMBVB. Yeah. So molarity of the acid, volume of the acid must equal to molarity of the base, volume of the base. IB are both 1 because your acid has 1 proton. So HCl has 1 single proton. So I is 1. IB is also 1 because this base can only accept 1 proton. It doesn't have hydroxide, but it accepts 1 proton. Same thing. So I just plug it in. Do you see molarity of the acid is 1.25 molar. The volume is 29.95 mil. That's how much HCl was used. And molarity of the base. My base is that sorbate, right? I'm looking for the molarity. And the volume of the base, if you go back up, you had 45 mil. That was part of the reading. 45 mils of the stock base was titrated with 1.25 molar hydrochloric acid. And look at the sig fig. It's 45.00 mil, yeah? So I want to carry out to 4, but then molarity is 3, so I want to carry out to 3 sig fig, yeah? And it's that easy. Moles of the acid must be moles of the base. And this is true at every single equivalence point. So the molarity base is 0.832 molar. Yeah, that's the answer. So that's titration. So you're not doing very difficult stuff. You just identify the 3 type of titration, so 3 BCA, and understand what it means. And the next one is that the pH at the equivalence point is 2.54, which indicator will be the best. Okay, so this is the concept of indicator. Okay, so do you remember the buffer equation that we wrote? pH of buffer. Buffer is a solution that has both acid and its conjugate base. The conjugate pairs must be both present. Yeah, there's a lot of ways to use this equation. First is for buffer. Okay, second, you can use this one. pH approximately pKa. So what this means is that this is the pH of equivalence point, okay, and this is the pKa of the indicator to choose. You want the pKa of the indicator to be as close as possible to the pH at the equivalence. This is a fact, okay? Indicators are buffers. That is another fact that textbook did not talk about. Indicators are buffers that change color, yeah? That changes color. When do they change color? At its pKa, yeah? So what I mean by that is, let's say I have 3 indicators. I have indicator A, this will dissociate into H+, and let me put this as indicator, yeah? How do I write indicator? INA, I guess. Okay, indicator A minus. So let's say the pKa is equal to 3. I have another, so what this means is that 3 is where it changes color, yeah? So for example, let's say this form, the acid is yellow. I'm making this up. And let's say the conjugate base, okay, the acid and conjugate base, right? Let's say this is blue. So it will change color from yellow to blue, blue to yellow, depending on the pH. And it changes color as 3. pKa is where it changes color. So in a medium, when pH is less than 3, you're going to have a yellow solution. If the pH is now greater than the pKa, which is 3, it's going to turn blue. So 3 is the indicator, color change, pH. So once again, pK of the indicator is where it changes color, yeah? And you want to use the indicator so that the pH at the equivalence point is as close as possible to the pKa. So all you have to do is now look at the choices. Okay, part C. Okay, if you look at part C, please, the pH at the equivalence point we're told is 2.54. So which indicator will change color for your titration, right? You have to pick one that is as close to 2.54 as possible. That's all. There's very little understanding here. You just have to pick the right indicator. So your equivalence point, once again, is a pH of 2.54. That is when you want to stop the titration. So you need an indicator to help you to stop the titration at 2.54. But you cannot see color change. So you got to pick the indicator. So the pKa must be as close to 2.54. So the best answer is that. That's it. Okay, you justify your answer by writing that right here. Indicator changes color at its pKa. Thymo blue has a pKa closest to the pH at equivalence point. That's your justification, yeah? Okay, so your buffer equation here can also be used to find the right indicator. Okay, so there's a lot of use of the buffer equation. And the next one, next question, it says, what is the pH at half equivalence point? We talked about this. At half equivalence point, the pH is always equal to pKa for any titration, yeah? Okay, except the strong one, yeah? Strong and strong is not really a titrate, well, it is titrating. It's not a buffer. So at half equivalence point, okay, your acid must equal to the conjugate base. So your buffer equation reduces to log of 1, right? When these are the equal, and that drops out. So pH must equal to pKa at a half equivalence point, okay? Because of this, okay? So what is the pH at the equivalent, half equivalence point? Not equivalence, okay? Half equivalence. So then you have the Ka. You see that in the beginning, you are given the equilibrium constant right here. You see that? The equilibrium constant is this. So 1.7 10 to negative 5. So what is the pKa? Negative log of that. And that will be the answer. So negative log 1.7 times 10 to negative 5. Yeah. Now, that is the answer. Now, I just want to point out one more thing I did not talk about. If you log something has 2 sig fig, your answer must be 3 sig fig. So look at here, I'm logging something that has 2 sig fig. 1.7 is 2 significant figures, okay? My answer for pH will have to be 3 significant figure, yeah? I usually don't care about it, but now we're going to start remind ourselves, we got to take out the sig fig correctly. If you log something with 2, you add 1. If you anti-log, you get rid of 1, yeah? That is the fastest way to do it, yeah? There's actually different ways you can do it. So 1.7, 10 to the negative 5, and I log it, so I have to carry out to 3 sig figs. That would be 4.77. That is the pH at half equivalent, okay? Right? So that's pretty much that, okay? And then, so then they want you to graph this titration, yeah? So you graph this one, that is pretty easy because you have the half equivalence, you have the equivalence. So let me just do this very quickly. Give me 1 more minute. I have the initial point of the titration. I have the equivalence. That was 2.54. And the half equivalence is going to be at 15, right? Because 30 mil to become equivalent. 15 here is half equivalent, and the pH we found was 4.77. So go to 4.77 right here, and I got to do a graph. So there has to be something like this. Okay, like that. So that will be the general shape for titration. And I gave you that shape last time, right? So again, your general shape titration is a little bit more detailed than this, but again, a half equivalence point, pH changes the least. So you want to be almost like horizontal, right? And equivalence point, you want to almost be vertical. And then there's a limitation here, what the pH can go. So don't touch zero here. Don't, yeah, okay. So it depends on the concentration of the acid, which we don't care right now. So that's about that. Okay, it's roughly that. Okay, so you want to grab something like this. This is a weak base titrated by strong acid, and the half equivalence point, the amount of base must equal to the amount of conjugate acid. So pH is always pKa, and that is always true at every single half equivalence point. And that's it. Okay, there's part F. I'll go over that, more titration next time. But today's lesson is important for electrochem. We cannot spend the whole lecture on electrochem anymore. So if you need more electrochem, watch today's lesson again. Okay, guys? All right, then we'll stop here. Thank you guys for coming in. I'll see you guys next time. Bye, guys.